Hi everyone, welcome to meeting 12 of Cryptography Club. We're going to talk about Euler's function and calculating phi. Euler's function. Consider this question. Given any positive integer n, how many of the positive integers less than or equal to n are coprime to n? For example, how many of the numbers from 1 to 8 are coprime to 8? To find this value, we can use Euler's function. It is expressed as phi n. From 1 to 8, the numbers 1, 3, 5, and 7 are coprime with 8. So phi 8 equals 4. Why the Euler's function is important? Because in RSA, we use it to find the value of phi n. Phi n does not always equal to p minus 1 times q minus 1, and there are many different situations. And after we talk about this, you're going to know why we can use p minus 1 times q minus 1 in RSA. The first situation, when n equals 1, phi 1 equals 1, because 1 is coprime with any number, including itself. So phi 1, the numbers from 1 to 1 that are coprime with 1 is just 1. So phi 1 always equals 1. Next, when n is a prime number, phi n equals n minus 1, because a prime number is coprime with every integer smaller than it. For example, 5 is coprime with 1, 2, 3, and 4, because from 1 to 5, it is a prime number, so there can't be any factors apart from 1 and itself. So if n is a prime number, then phi n is from 1 all the way to n minus 1, which is n minus 1 amount of numbers. When n is a certain power of a prime number, phi n will equal phi p to the power of k will equal p to the power of k minus p to the power of k minus 1. For example, phi 8 equals phi 2 to the power of 3, which equals 2 to the power of 3 minus 2 to the power of 2, which is 8 minus 4, which is 4. This is because a number can be coprime with n only if it does not contain the prime number p. And there are a total of p to the power of k minus 1 numbers that contain the prime number p, which are 1 times p, 2 times p, 3 times p, all the way to p to the power of k minus 1 times p. After we remove them, the remaining ones are the numbers that are coprime with n. So that's why we remove p to the power of k minus 1 from p to the power of k. Also, this equation can also be shown like phi p to the power of k equals p to the power of k times 1 minus 1 over p. This is basically the same as this, because if you multiply p to the power of k into the brackets, you get p to the power of k minus p to the power of k minus 1. So that's the formula we use for when n is a certain power of a prime number. Next, when n is the product of two coprime integers. So if n equals p1 times p2, then phi n equals phi p1 times p2 equals phi p1 times phi p2. For example, phi 56 equals phi 8 times 7, which equals phi 8 times phi 7, which equals 4 times 6, which is 24. So because 8 and 7 are coprime, we can turn 56 into 8 and 7. So phi 56 equals phi 8 times phi 7. Apart from all of the different situations, there's also a general formula we can use. Any positive integer greater than 1 can be written as the product of a series of prime numbers. So any positive integer greater than 1 can be written as p1 to the power of k1 times p2 to the power of k2 all the way to pr to the power of kr. The general formula says that phi n equals n times left bracket 1 minus 1 over p1 close bracket, open bracket, 1 minus 1 over p2 close bracket, and then multiplied by everything until open bracket 1 minus 1 over pr close bracket. For example, 5 1800 equals phi 2 to the power of 3 times phi 3 to the power of 2 times phi 5 to the power of 2. We got all of these numbers by prime factorizing 1800. And then, so 1800 equals 2 to the power of 3 times 3 to the power of 2 times 5 to the power of 2. So we took all of those and put them into separate phi's. And after we do that, we can use the general formula. So that equals n, which is 1800, times 1 minus 1 over p1, which in this case is 2, so 1 over 2. And then times 1 minus 1 over p2, which is 1 minus 1 over 3. And then pr is 5, so it times 1 minus 1 minus 5. 1 minus 1 over 5. So all of these multiplied together is the value of 5 1800. So this equals 1800 times 1 over 2 times 2 over 3 times 4 over 5, which is 480. So there are 480 positive integers from 1 to 1800 that are coprime with 1800. And that's the general formula. Next is modular multiplicative inverse. If two positive integers a and n are coprime, then it must be possible to find an integer b such that a times b minus 1 is divisible by n, or, in other words, the remainder of ab divided by n is 1. And mathematically, it's shown like this. So ab mod n has a remainder of 1. And in this case, b is called the modular multiplicative inverse of a, and there should be an infinite amount of values for b. In RSA, this is used to find the private key d, because when we're finding d, the restraint is e times d divided by phi n has a remainder of 1, and there in RSA, this d is basically the same as b in our example. So there will be an infinite amount of d's, and we just pick a relatively big one so that it's harder to crack. So in RSA, we use modular multiplicative inverse to find the private key d. Let's look at the code for today's meeting. This code is just to find the value of phi n for any number of n. We have two functions. The first one is phi n. So we define phi n. And then inside the phi n function, we have the coprime function, which is the same as the function we used in last meeting. So it takes in the parameters n and m to compare to see if n and m are coprime. At the end, it returns true if the two numbers are coprime and returns false if they're not. The value of n and m doesn't matter, so you can make n the bigger one or you can make m the bigger one. Because even if m is the bigger one, it will automatically flip inside the function, because we have this loop. While m is greater than 0, we give the remainder of n divided by m to t, and then we give the value of m to n, and n is the greater numbers or like the variable. And then we give t, which is the remainder from here, to m. And then we continue this loop until m equals 0. That means that there is a multiplicative relationship between two numbers. So one is a factor of the other number, and then we stop. At that point, if n equals 1, that means the two numbers are coprime. If not, then they're not coprime. So this is the function that we use to see if n and m are coprime. After we have this function, this is the part that we use. This is where we run the function inside the function of phi n. So inside the phi n function, this is the number that we're trying to find the value of phi for. We give that number to the variable num, and then we set count as 0 because we're going to add stuff to it later. And then we have a loop from 1 to num plus 1. So this is basically from 1 to num, which is this phi number. And then inside each loop, we're going to see if I and the num is coprime. If they are, then we print I and num and the string coprime, and we add 1 to count. If it's not, then we just skip this and go to the next one. So if we started with 1, after the first time, it's going to turn into 2, and then we compare 2 with the number to see if they are coprime, all the way to the number itself, which we know will definitely not be coprime, but we still do it anyways. After we finish all of the loops, we return the count, which is the amount of numbers that we found that are coprime with n. So that's the value of phi n. So that's the function we're going to use. And then here is the running the function part. We have p equals 61 and q equals 53, and n equals p times q. We're going to first print phi n and use our function. And then we have the phi check variable, because we know that because 61 and 53 are both prime numbers, we can use the situation for prime numbers, which says that phi n equals p minus 1 times q minus 1. So we're going to print phi n using our variable that we created, or our function, and phi check, which is checking to see if the two numbers match. If they do, then our code is successful. So it's comparing all the numbers from 1 to 3,233. And then we can see that on the left, these numbers are all coprime with 3,233, and they're mostly continuous. But we can find like a gap between them. That means that one of the numbers is not coprime with 3,233. Yeah, for example, between 3,126 and 3,128, there should be a 3,127, but it's not here. That means it's not coprime with 3,233, and that is one of the numbers that will get included into the count over here. So, wait, no, that's one of the numbers that won't get included into the count. These numbers are all included into the count. So these numbers are all coprime with 3,233. And then at the end, there are 3,120 numbers that are coprime with 3,233. And the phi n is the same as the phi check. So that means that our code was successful. So phi 3,233 equals 3,120. And then let's try. In our code, we used an example when n was 1,800. So let's try that. Because 1,800 cannot be factorized into two prime numbers, so this phi check cannot be used because it doesn't have a situation where we can turn it into p minus 1 times q minus 1. So we're just going to run the phi n and see if it equals 480, which is what we got over here by using the general formula. so it does equal 480. That means our code is correct. Thank you.